And we'll talk later about like the redesign of the DSL I want to do. It's going to make this a lot clearer. But right now, because the class abstraction is obscuring a lot of this, it's not obvious that that's not what you would have to do. It's hiding the preconditions from you. So you don't see what's going on with preconditions.
So what's the deal with the limit of account updates per single hold? There's 7 to 9, something like that, right?
Yes. That has to do with a couple of factors. The biggest one is transaction size. The more account updates you allow, the larger the transaction size is. The other one is the way that we're doing it in the scan state. Sorry, that big queue structure is the scan state. The account updates are not embedded into there. I'm going to try and explain this without redrawing it because I want to redraw the whole thing.
I don't remember.
But basically, in the future, you'll be able to prove those account updates in parallel. Right now, within that one work item for that transaction, you have to approve all the account updates. So if you allowed an unbounded number of account updates, not only could the transactions become way too large, or the chain, it would hurt the chain, but in addition to that, it would also create a bottleneck in the prover queue because you have to prove all those account updates before you can continue the next transaction in the queue. Does that help? It's something to fix in the future.
Well, it's not that the blocker because you can just kind of do a new method on top, but just
there's things you can do.
Experience.
It just makes it annoying, right?
Yeah.
So it's something to fix in the future. I don't know if we'll ever get to the point where you have an unbounded number of account updates because of the transaction size issue. You don't want to have an unlimited transaction size. That's really bad. You could take down nodes by setting gigantic transactions. But I do think that we can heavily increase it. Doesn't need to be 8. That's like a now thing. Real quick, I'm just going to wrap up by explaining what a method call is. Whenever you're calling a method, you're generating a proof for that next step. So if this was a method call, you're generating a proof for the token. Not only is this more expensive for you to do computationally, it's also going to make your transaction cost more money. Every proof is going to change the weight of your transaction. We have this concept, because we don't have gas, we have this really cool thing we can do, where we can look at this list of account updates and know exactly how much work it costs the network. In other words, we actually weigh the transactions by the amount of work they're going to incur. And then what we're actually looking at in the mempool is the fee divided by the weight. So because we don't have gas, it's really cool that we can do this, and it's a cool feature of the chain, but it also means that the more proofs you're stuffing into an individual transaction, the more fee you're going to have to pay in order for your proof to be competitive, because somebody who pays the same amount of money for a transaction with 2 proofs, but only have a transaction with 1 proof, their transaction is cheaper than your transaction. Does that make sense? Because the weight of your transaction was heavier.
But then you have recursion, right? You can just recursively prove your own.
Yes, you can. But if you do the method calls, you're not doing recursion.
Cannot I write a separate method that proves those 2 methods?
You would have to do it as a zk program.
Yeah, that's what I'm thinking.
Method calls in the smart contract layer right now are all separate account updates that have proofs attached to them. And so in the example I was giving before, like I said, you probably have token up here and holder down here. Usually it's a more sensible way to do it. But if like I was doing this, if I had to do something in the holder where I had to check a predicate of the holder from the token owner, then I don't actually want to know the token, the token holder's contract and have to execute that code. And B, I don't want to pay for the proof. It costs me more time. It costs me more money. Like, it's not necessary. Each of these account updates is a slot for me to look at things on the chain. I don't need a method on a smart contract to read state from the chain. Methods on smart contracts are for generating proofs.
Is every method compiled or to create a proof, their compilation of 2 circuits or constraints are used? I mean, is every method is compiled in some step to circuits?
Yes.
Okay.
Yeah, every method is its own zero-knowledge circuit.
Mm-hmm.
What a zk program is, or a smart contract is it's a recursive layer on top of all the methods. So every method is its own zero-knowledge proof, and then we tie that together with a layer of recursion so that you can basically fold them all into one verification key at the end. That's what's actually going on. the proof that you attach is actually the recursive proof verifying whatever method you did. That's sort of like, it uses this thing called a side-loaded verification key to do that. So rather than saying, this is the verification key I'm going to verify, the verification key becomes an input to the start proof. And then that allows you to say it has to be one of these verification keys, you know.
If I have a smart contract with one single method, do you still have to recursively create verification key of it?
You do. But it's you don't think about it that hard. It's not terribly expensive to, but this is the way that pickles and kimchi works. Actually, for reasons, because there's like two different curves that you're operating on, even the blockchain proof is proven and then recursively proven again. It's an implementation detail of recursion. You have a pairing of like two different curves. Anyway, I'm not an expert of it. I can't talk about that much. Don't ask me. There's a lot of back and forth between two different proof systems in a sense all the time. One for recursion, one for logic, sort of. That's part of how we do it efficiently. Whereas other proof systems have a harder time if they don't design it this way. But yeah, you should ask other people who know cryptography. Okay, so now I'm going to talk some about actions reducers, what they are, why you would use them. So far, all the stuff we've been talking about, this is basically how the L1 zkApps work. Okay, this is compared to Ethereum, because you're always doing the proving and the user space separately from the sequencing layer. It's basically a highly concurrent computer. And being a highly concurrent computer, you run into all the issues that highly concurrent computers have regarding race conditions, right? You experience race conditions at the L1 layer. Because what we've done is we've explicitly removed sequencing and execution from each other. We divorced the two. Actions and reducers is a pattern to basically put sequencing back into the execution. That's the way you can think about it. So the idea is that you have this decentralized consensus mechanism that does sequencing, and you have this off-chain execution system that can do execution. Actions are the way to allow the L1 to sequence what needs to happen, while off-chain work can happen to execute the sequence that was agreed to. In other words, you're using actions to bootstrap off of consensus. Does that make sense? Consensus is the system through which the network achieves, consensus on what the sequence should be. And then you're using that agreed upon sequence you have submitted to then execute the order the network has agreed to. And so the way that works literally is you can just think about actions like a queue. Every account is storing a Merkle commitment to the head of the queue. This is just a Merkle list, okay? And when users go and they submit actions to the queue, these get ordered into the queue by the network. So when users come and they submit actions, they're just submitting transactions and saying, I want to push to the end of this queue. But maybe the network defines this order based on the order it received it in, or maybe, these two get swapped because of the order the node is in, or it has to do with the transaction fees. I basically don't know what the sequence is going to be until the network has run for a bit and come to consensus on this. At the point that the sequence is committed to, a reducer, which is just a basically recursive proof for a zkApp, can go through and it can roll the execution of all of these things up and bring it back to the head of the action queue. Okay? And that's really all actions reducers is. It's just a concept of like using a Merkle list on chain to define a sequence that you want to execute things in.
It's not a counter pattern that it's been added to make life easier. It's a proper pattern that should be used.
Yeah, it is a proper pattern that should be used, but today it's a little too hard to use properly. So we'll talk about what's wrong with this pattern today and what makes it really hard to use correctly and the mistakes that most people are making. I think of the teams I've seen build zkApps, and I haven't read everybody's zkApps, the only team that's figured out how to actually use this correctly is Protocol.
Interesting. My whole zkApp depends on it, so yeah, you can take a look later.
I'll give you some pseudocode later too that fixes it. Okay, so implementation detail. if we were to off-chain reduce everything in this list and commit back to this this head of the list right here for the action queue, well, by the time we actually submit it to the chain, what if like new actions have been submitted? Wow, what a bad square. Well, now the thing I committed to is not actually my account state anymore. I'm making a precondition on the fact that I've connected back to the head of the action queue, but the action queue's moved since then. In other words, the action queue has the same kind of race condition issue that anything in the network has. The way the network gets around this is the network actually stores 5 positions from here, which are basically what the state of the action queue was at the end of the last 5 blocks. And so what this means is like, if F was the head of the action queue, and the queue moves, well, as long as I get to submit within 5 blocks, then it's still good. The problem with this is that it's only the last 5 blocks, right? I'm only allowed to look at the last 5 blocks. So imagine now I try to do this operation, but it was too slow, or my server went offline for a bit. And now I've lost all of these. I'm way far in the future, and none of the last 5 blocks have this anymore. So now I have to redo this operation, and I have to catch up. That might be fine. I can maybe keep on doing this. I have more and more things to recursively prove, and eventually I will connect it back to the head of the queue. But there's an interplay here. Side effects. As we mentioned before, there's a hard limit on 8 account updates per zkApp transaction, right? That hard limit means, imagine like I was just doing something really simple, like an airdrop. Okay, this is just the simplest example. So each of these was a flame and an airdrop, and I have a Merkle tree of nullifiers. That's how I check double spins that I can only withdraw once. I'm going to use actions reducers because every user trying to interact with that tree is going to have a race condition. So then I'll use these. But every time I reduce an action, I have to push an account update to send them tokens. If I have more than 7 actions here to process in one transaction, I can't fit them all in a single transaction anymore. And so if the queue has moved so far ahead, there's more than 7 things I actually do here, my zkApp is just deadlocked. There's no way I can ever reach back up to that queue because I've hit a different limit related to the side effects I was doing here. And if I relax those side effects saying, oh, I'm just going to skip them, well, then I'd ruined censorship resistance because now my application can arbitrarily just censor people's attempts to withdraw airdrops, which is the whole point of this action queue, is we're trying to get censorship resistance through the L1, right? And so in some cases where there's no side effects, this might be fine. But most applications have side effects. Most applications are sending people money. They're looking at different things on the chain. They're looking at other states of accounts. They have interactions that have to go with processing this individual action. And because of that 8 account update limit, it means that I'll basically deadlock if I ever get to the point where I'm overflowing that 8 account update limit within the number of actions I have to reduce. And I can't reduce the actions up to some partial point. I have to reduce it up into what the action queue was at some point in the last 5 blocks. Even assuming my app was online all the time, if I got more than 7 transactions that submitted actions in a single block, I'm still screwed.
2 things here. If I remember correctly, you still can only query the actions from particular action hash, so you can get a subset of actions in the past.
But you can't prove that it was actually related to the action queue you have on chain.
Let's see. I guess
There is this trick you can do where, let's say I wanted to process 3 transactions, and now the queue is like up here. Well, I could produce a Merkle proof saying, oh, this was existentially in that chain, right? But the problem is that proof is O of n. And if I'm doing that proof n times, it's, sorry for writing sideways, O of n squared. That sucks. I don't want to do O of n squared operations.
like if I always start the last processed action hash within my zkApp, I could always go back to it and not.
Which is exactly what you have to do. But now imagine I can only process 3 actions. So I'm going to move it to here. But I don't know without proving this connection that this was actually part of the queue. My application could just arbitrarily choose any sequence of actions that's not connected to the queue. I have to prove it's somehow connected to one of the queue points that was committed to in the last 5 blocks. And that's where the O of n squared thing comes in. You can do that, but realistically you can't. O of n squared proofs is crazy. There is a solution to this. You can solve this, but it's not an out-of-the-box solution, and it's not provided by O1JS. Okay. So let's say I want to choose an arbitrary number of actions from the queue and efficiently reduce just a set of actions I choose. Like I want to say I'm going to reduce 3 actions from the queue. Okay. Here's how you can do that. And I can provide some pseudocode for this later. And this is exactly what ProtoKit does too, by the way. What I can do is, this is the head of my queue right now. And that queue is going to keep on building here. But what I can do is, I know that this is the last point I process to. And I know that this is a point that I want to process until. I can take a snapshot of that. What I do is I actually snapshot all this information. So I just have that portion of the queue right here. Let me get these names. Okay. But now I'm back in the O of n squared problem still. Because if I want to pull just one action off here, then I have to do n-1 recursive proofs to prove it's here. And then I pull the next option off, I do n-2 recursive proofs, n squared, right? So there's this other trick that you can do where you then take the snapshot and you produce a Merkle proof of the reversal of this list, okay? Merkle lists are just linked lists. As you know, an index operation in a linked list is O of n. And so if you do n loops of O of n linked list indexes, that's O of n squared. But now that I've reversed it, popping off the head of a queue is O of y. And so I can say I'm going to do A, I'm going to move the pointer. I'm going to do B, and move the pointer, and it's O of 1 now, and this just becomes an O of n operation instead of O of n squared. And so the trick is to take snapshots to reverse them so I have a stack that I can pop off of, to pop off that stack in increments that I can handle until eventually this is empty, and then I take another snapshot. But if you don't build your contract like this, your contract is susceptible to deadlocks that you can't control. Users can make your contract deadlock.
I see. You mentioned this is not possible to make snapshot in O1.js, right?
No, it's possible to. It's not provided by the action reducer toolkit in O1.js.
I see, because I know that
you can't use the action reducer pattern that exists in O1.js, like there's like the reducer you can include in your contract. You can't implement it with that.
So maybe we're going to talk about that, but can we talk about the storage aspect of this? Like, what's the best way of storing those without actually decreasing decentralization and, like, I don't know, decreasing liveness?
Well, actions are stored inside of the archive node.
Yeah, but do you think like that's the best solution possible? Because in that there are no incentive mechanisms for archive nodes, and like saying that the applications that need actions and reducers should run their own archive nodes, and I don't know, like, is this a fair model?
I mean, the incentive is that explorers have to run archive nodes and provide the data. But there are ways you can integrate with other data availability platforms like Celestia and things like that. That is totally possible, and we are talking with Celestia about that. But honestly, I'm personally not totally convinced it's that necessary. I think the incentives to run archive nodes and provide the data are already there. There are app developers that need to run them. There are explorers that need to run them, and explorers have business models from running them. So, like, I'm not as worried about the data availability problem of actions because there is data availability provided through the blockchain history, and there are so many incentives to run the blockchain history. It's only in a world where everybody stops running archive nodes and decides that they're going to paywall the databases to actually like access this information that it's actually an issue. And we are still looking at the data availability solutions that are more like robust, but I'm personally not that worried about it. I don't know. You can tell me if you're worried about it, but I think it's actually not that important. It's sort of like you're basically saying like, you only need one person to provide you the data, right? You're not trusting an entire network of people, and you're not actually trusting them at all because it's Merkleized data that's been committed to on chain. They can't lie about the information they give you. They can only refuse to give you the information. So it's the world in which everybody has decided they're not going to provide archive node data that you would live in, that you couldn't do this. That's my opinion. But yeah, there will be integrations with other data availability providers. I'll get on this. I'm going to talk about side effects now some more, because there's another issue with side effects that you'll also have to think about with your contract. So going back to the situation where you want to do an airdrop, let's ignore actions reducers. Let's say you're fine with the race conditions. That's not the issue. Let's just say that you have, some contract that wants to send, it doesn't have to be a token. It can just be 5 Mina, okay? It's back to that same 5 Mina problem. There's an issue with this. Well, actually, I will talk about the context of action reducers because we'll just talk about it like that, right? You have some sequence that's been committed to. You have to process this. A has to do this thing. Otherwise, A can't do anything else that's been in queue, okay? So A is stuck doing this thing. They're committed to doing this thing. They have to gear it, okay? Otherwise, their application can't continue, right? Whether it's through actions reducers or through other application logic, this is like the next step in the computation is they have to do this step, right? There's an issue that imagine B is a user account and A is the smart contract account, okay? What if B sets the receive permission to none and then asks you for 5 Mina? And now you have to send them 5 Mina, but you can't because their permissions have actually disallowed you from doing that. Like, you basically, if B sets, because we have all those permissions that you can set, B sets receive equals impossible. Or even if B sets receive to signature, right? It's like, oh, you have to have my private key to do this, Like both those situations, if you're A, you're just like, well, I have to do this thing. You've told me I have to do it. I've allowed you to let me do it. And now I can't process it. Well, naively, maybe one way to solve it is like, in order for B to submit the action, B has to prove that its permissions are valid, but B can just change its permissions afterwards. They're concurrent. Nothing stopped B from changing its permissions if I'm just setting up a regular Mina account. B can come in and do this and now deadlock my contract arbitrarily. And so this becomes an issue, a design issue with the chain. And I have a few different solutions for this, actually, that I'm hoping to, maybe I'll workshop it later. One of them is zkApps. We'll talk about that later. But the issue here is that, like, if I just naively design my smart contract to allow people to come in and request withdrawals, and then I'm committed to the fact I'm going to do that withdrawal, they could deadlock my contract, and it's outside my control. And so in your smart contract design, you have to carefully design around this today. This is not a problem with other chains. It's something that we have to think about when we're actually designing our smart contract. There's a few ways to do it. One way is to have permissioned accounts. This is what ProtoKit does, okay? What ProtoKit does is ProtoKit says you can't come and ask for a withdrawal from any account. You have to come and ask for a withdrawal from an account that I made for you, or you could ask me to make for you. And what that does is there's this whole token parent-child relationship. If you remember the call stack, when you have a token parent-child relationship, anytime I do an account update on a child, I have to generate a proof from the parent to make that account update. In other words, I can't just update the child directly. I have to go through the smart contract logic. And so this makes it so that you can ensure they don't send the permissions in a way that you can't handle. That's one way of solving it. But it requires you to keep on allocating accounts in the ledger, right? Now I don't just pay 1 Mina account creation fee for my account. I have to create 1 Mina account creation fee for every ProtoKit app chain I interact with. They're all separate. They're all different settlement contracts. They're all going to require additional accounts for interaction. And I'm going to have to keep on paying that per application I interact with. And that's money down the drain that I don't want to spend. It's a bad user experience. I have to know that I have this account and reuse it. Now I'm controlling a bunch of different private keys. I'm not just controlling one private key. It's a big pain in the ass. Actually, you can get around the private key issue, but that's beside the point. So that's one way of doing it, is with this parent-child relationship called permission accounts. The other way of doing it is by always making a new account. In other words, if B asks me for money, A doesn't actually send money to B. A sends money to some new contract, C, that's deployed, and B has permission to take that money out of C. Okay, if B comes along with its private key and generates a proof against account C saying I own the private key for B, then B can transfer the money out wherever, right? Well, this is also annoying. This is actually even worse because permission accounts were at least reusable, even though they're paying. This one, the contract owner has to keep on paying for it. Maybe they can charge the user who submitted the action, but it's 1 Mina per interaction now, not just 1 Mina per space that I can do interactions in, right? And so both of these solutions are not great. What I'm working on implementing right now in the protocol with the protocol team is this idea of deletable accounts. and then this pattern called consumable accounts, which are accounts that you allocate that have to be deleted, and you get a refund when you delete it. And that is used to then build zkPromise, which is like a concurrency abstraction for sequencing updates that need to happen afterwards. And so the idea is that basically you could do the same pattern here. This doesn't exist right now, but I hope it's currently slated for the next hard fork. We'll see if it makes it or not, but I think it will. Next hard fork should be in about 6 months, by the way, for people's context. Will not be as painful as Berkeley. And so the idea is that you can do the same pattern, but when B pulls the money from C, it has to delete C, has no option. And that refund would go back to A, or maybe you go back to B, depending on how you program it. You can program where the refund goes for the account creation fee. In addition, maybe what you could do instead is like, if I put this 5 Mina here and B never withdraws it, I could have an expiration in slots where A can come back in and take the money back. Like, you can basically write this as programmable logic for C that's like, okay, either let B withdraw it, or if it's been like 100 slots and they still haven't withdrawn it, then anybody can come in and refund it back to me, right? So you create this whole system of logic for like refunding the fee, who you're sending the fee to. Maybe the way this actually works is that B, when it submits the action to A, is going to give the 1 Mina, and then we're going to give 1 plus 5 Mina here, and then we get 1 plus 5 Mina back out. So it's like basically the cycle of how we're transferring the money that was used as a bond for allocating the account. And so this is what I want to work towards now on the protocol, and that's the pattern I think is going to make the most sense for the immediate future. Even past that, I think there are other ways to solve this problem, but this problem just kind of comes naturally from how permission model is. And I would argue this is not a bad thing that our permission model is this flexible. It's actually really the power of the protocol that you can do this, but it introduces a new set of problems. On EVM, you could implement the same kind of system without having the issue, because in EVM, you can do try catch. It's like, I'm going to try to send the money. Oh, I couldn't. I'm going to handle the error and skip it. You know what I mean? Like, that can be codified in the logic of the contract. But on Mina, you sort of only go forward. It's like linear. You can only move forward, right? There are other things you could do, like looking back that the transaction failed. You could try and prove that you tried a transaction and you couldn't process it, but those are really painful. They hurt throughput of your smart contract because you have to try something and then prove that it failed later. This is the way forward to actually like let the contract just move forward, because the whole point is the contract wants to do something and then the contract wants to unblock the rest of the actions that are in the sequence.
Just to clarify, this exists in all cross-application state updates, right?
Yes. Yeah, basically every single one, because there's also this really nasty permission called access. It's used for token parent-child relationships. But what this access permission does is basically mean you can't even put an account update against that at all. All account updates that attempt to look at this account will fail. So it does exist for any interaction, even if you're just doing a precondition.
With these sets of problems, and then the attention moving to how to kind of do the workarounds with like ephemeral or refundable accounts.
Mm-hmm.
Was there some thinking around the permission model that would handle this scenario up front, or like when did this sort of arrive, and was there an exploration that didn't involve the workaround? Basically, I'm interested to understand that.
So I thought about it. So I had conversations with Matthew about it. The problem is this permission model is really powerful and really important. Anything you do to weaken this might solve some use cases for this problem, but not all. You're just sort of like shaving off some problem areas at the cost of like weakening the permission model. And the permission model is actually really powerful. It's actually a good thing. Some things could be weakened from it. You could argue that some things are not necessary. Maybe this access permission can be modeled a different way. But even if you fix this access permission, you still have these other permission issues. And even if you fix these permission issues, you still have the issue with the subproofs. If I can't generate a subproof, I can't send the transaction at all. And so no matter what you do to the permission model is an example of what can go wrong with this. But the problem is bigger than the permission model. So even if you deleted the whole permission model, you still have this problem.
You still have a subproof problem.
Exactly. And so I basically decided that messing with the permission model is not the solution here. the solution here is an architectural day. And I think there's other ways to solve within this. This is like a very straightforward path forward. It can be wrapped up in a pretty nice way in O1.js that people don't have to think about that much, like the ZK promise idea. But long term, I think there are other ways that we can think about fixing this. There's like certain limited forms of on-chain execution can help with this. Having like try-catch logic that's available and accessible in account updates is a way to deal with this. But, you know, all of those still have sort of some issues regarding like executing subproofs. So the only one that completely removes the subproof issue is the ephemeral account ones. Because in the ephemeral account, the subproof execution happens by C, by another party that has to come in and finish the computation. Or it could happen by A, but like the point is that you separate it out of the state machine for the reducer, so you don't deadlock the contract if there's an issue processing the side effect.